Alright guys, so let's get into our next unit here, continuing with the trig, but instead of just using right triangles and finding sides and angles and unit circles and all that stuff, let's talk about what does the graph look like. You know, what if somebody said to you, I need you to graph y equals the sine of x or something, or y equals the cosine of x. Okay, or you know, if there were transformations, you know, there were shifting or stretching or reflections and all that stuff, we're going to see how to handle all that stuff. And what we're going to do is actually kind of really simplify it. And one good thing, when you don't know what a graph looks like, you can always make a table of values and plot the points, you know, and then see what they end up with. So let's think about what these things look like. And the good news is we are only going to use, okay, going back to the unit circle, right? We are going to use just those 4 points that I outlined. Okay, now we could obviously get more accurate and plot the 30 degrees, 45 degrees, and every single one of them. But let's just use these here. Okay, so 1, 0, because remember the unit circle is centered at the origin with a radius of 1. Let's see, so 0, -1 down here. Okay, and let's start out by graphing the sine of x. Okay, so what we're going to use, the x right here is actually going to be the angle measure. Okay, so the ones we're going to use are the 0 degrees, 90 degrees, 180 degrees, 270 degrees, and then 360. And 360 is just going to get back to where it was at 0. Okay, and let me just say this, most of the time when we're doing these problems, it's going to be, instead of in degrees for x values, we're going to be using radians for the most part. But let's just start out with degrees for now because we're more comfortable with it, I think, and you know, it's just more familiar to us. So let's think about, okay, if y in this case is the sine of the x, right? Because that's the one we're graphing first. We'll graph cosine later. When x is 0 degrees, okay, so 0 degrees, remember these are all degrees, what is the sine of 0 degrees? Well, the sine of 0 degrees is just the y coordinate there, okay, so 0. The sine at 90 degrees, the sine is always the y coordinate. Okay, at 180 degrees, the sine is the y coordinate. At 270 degrees, again, the y coordinate. And then when we get back to 0 degrees again, the y coordinate again is 0. Okay, so just keep those points in mind. We're going to go ahead and plot them in a second. And let's do it. I have a graph set up here. Actually, I'll just do it on this page as well, and we'll fit it in a little better. But the way these are going to look, your x values are going to be, in this case, 90 degrees, 180 degrees, 270 degrees, 360 degrees. And what's going to end up happening is, like, actually, let's plot what we have. Not get ahead of ourselves, and then we'll talk. So, so the first point from my table is 0, 0. So this one's going to start at the origin. Okay. By the time we get to 90 degrees, the y value there from the table is 1, right? So that's the sine of 90 degrees. When I get to 180 degrees, the y value is 0. Okay, by the time we got to 270 degrees, the y value was -1. And then back to 360 was back to 0. And so you get this, it's kind of a nice smooth, rounded, you don't want it to be like straight edged, you know, it's more rounded, nice and smooth. And the good thing is, or the cool thing, I guess, that's unique about these is once you get past 360, as this thing keeps going, imagine once you get past 360 degrees, right, once you're here and you keep going, you're just going to repeat those same values again. So it's just going to kind of do the same pattern again, on and on, okay? And it does that in both directions because you can go negative and it would just be going this way. And that's the cool thing about these. They're called periodic functions because they just repeat themselves, okay? In this case, every 360 degrees, you're going to be doing one full circle. So you'll be doing one of these. This is considered one cycle from there to there, the yellow part. And it will repeat itself on and on infinitely long. Okay, and that's what's new about these things. We haven't seen any functions that, you know, you graph it and then it just repeats itself exactly the same, goes through the same y values again. Okay, so when we graph these, I'm going to ask that you show one complete cycle. So let's get this one a little neater on the with kind of where they came from. Again, it's just choosing the 4 values on the unit circle, the 0, the 90, the 180, the 270, and then the 360 again is where it starts to start over. And just deciding, if it's a sine function, right? So one last thing, if it's a sine function, you're using the y coordinates. If it's a cosine function, you are using the x coordinates. Okay, just like on the unit circle, right? The y was the sine of the angle, the x was the cosine of the angle on a grid here, and then we'll talk about what cosine looks like using the same concept. So again, let's label these. We're just going to really use 4 little marks on the x-axis here. Okay, and in this example, we only needed 1 and -1 for our y values, right? Okay, so the sine, if you remember, it started at 0, 0, went up to 1, back down to 0 when we were at 180, 270, and then 360. So it does one of these guys, right? I'll throw a little arrow on there. We know it's going to keep going. Okay, and that's considered one cycle. Okay, so you can see the y values are always in between 1 and -1. Okay, and then so that's going to be the range, right? The range is what possible y values do we go through. And then the x values, the domain, this thing goes on forever and ever. So the domain is actually all real numbers. But the range, right, like we said, is always between -1 and 1. If you look at the graph, it never goes higher than 1, never goes lower than -1. Now that can change, okay, if you have multipliers. If we multiplied this by something, it would just vertically stretch it, kind of like how a slope changes thing, even though it's not really a slope with this kind of thing. But it would change the range. Now the domain for these will always be all real numbers. Okay, so let's think about what the cosine graph looks like. And I'm gonna do the same thing. I'm gonna draw the circle again just so we have it right in front of us and we can use it. So real quick, there's our unit circle. And the 4 coordinates again, we're just going to use those 4, same as before, 1, 0, 0, 1, -1, 0, and 0, -1. Okay, so let's set up our x-axis the same way, 1, 2, 3, 4. So you're always going to divide it up into 4 pieces, 90, 180, 270, 360. We're going to be between 1 and -1 again. Now here's the difference though. The cosine of x means we need to be using the x coordinates here, right? So I'm going to start out when the angle is 0, right? A 0-degree angle is right here. The x coordinate there is 1. Okay. By the time we get to a 90-degree angle, the x coordinate, the cosine of 90, is 0. Okay, by the time we get over to 180 degrees, the x-coordinate is -1. Okay, so that's the cosine of 180. By the time we get to 270, the x-coordinate, or the cosine of that, is 0. And then getting back to where we started, the 360 is the same as it was at 0, so it gets back to a y value on the graph of 1. Okay. Now here's the thing. This is tempting to maybe draw this one like a parabola or even like an absolute value v, but that's not the case. Okay, because what ends up happening at 360, it's gonna start going back down because 360 is gonna match up with what was going on at 0. And what needs to happen is you need to draw this like a nice smooth curve, but make sure the last one is the maximum and it starts to come back down again. Okay, and what I'm trying to show you is that this part right here is matching up with this part. It's not going up still, it's coming back down because at 360 is where it's starting to do its full cycle again, right? We do the full 360 and then it's going to keep going and just do the same thing again. Okay, so those are the parent functions for sine and cosine. Okay, they both have the same domain and range. Okay, one thing to tell them apart is that sine is always going to start at what's known as, okay, if you think about, let me just draw these here, 1, -1, right? That's the minimum and maximum. The sine always starts at its midline, it's called. Okay, the maximum's 1 and the minimum's -1, like the average of 1 and -1 is 0, right? So the sine curve starts out at 0, while the cosine curve actually starts out at its maximum. Okay, it's not starting out at the middle or the minimum, it's starting at its maximum. Okay, so that's how these things kind of differ a little bit. So let's add one thing to the mix. Okay, let's do a couple examples using the parent functions. And if you need to graph one of these functions, and it's not just the parent function, right? It's not just y equals cosine x or y equals sine x. What a good idea usually is to draw the parent function on your graph, draw one of the whichever one of these two it is, and just do that as like a nice dotted line or do it real light, and then we will just make the adjustments needed. Like for example, this one is multiplied by 2, as you can see. So let's see what's going to happen. So I'll use yellow. I'm going to graph the parent function first, which is just y equals the cosine of x. Then we'll come back in and see what impact the 2 has on it. Okay, so let's graph this one first. I'm going to set up my 4 tick marks here, and I'm using yellow. I know it's a little tough to see, but this is just like a basic intro for us. This is not going to be the final answer. 1, -1. Okay, so what does a regular old cosine look like? And again, I would suggest, especially when you're first seeing these, which probably is most of you for the first time right now, think about the coordinates of the 4 main angles there, 0, 90, 180, 270. And since we're talking about cosine, right, we will be using just the x coordinates. Right, so that's going to tell us where to go. So on the graph, when the angle's 0 degrees, the cosine there is 1. Okay, then I'm just going to work the pattern around. Then it goes to 0. Then it goes to -1 down here at 180. By the time we're to 270, the coordinate's back to 0. And then 360, we're back to 1. Okay, so this right here, this is going to be the parent function. Okay, and again, that's not my final answer. All that is, that's just recreating what we did right here. Okay, so I have like something to work with. It's just kind of like a guide, right? Okay, so that's that. Now it's going to be easier to figure out, all right, what does that 2 do to the graph? So the idea is when you multiply a function by 2, okay, if you recall, it vertically stretches. Okay, technically what it's doing is just multiplying the yellow graph. It's going to multiply all the y values by 2. Okay, so what it's going to do, it's going to take each of these points. Okay, like for instance, this first point right here, it's going to get multiplied by 2. Its y value originally is 1. If I times that by 2, it's going to be 2 now. Okay, and I'm just going to go through, we plotted 5 points, right? So that one's up to 2. The next point was at 90 degrees, it was at 0. Okay, if the y value is 0 and you times that by 2, it's still going to be 0. Okay, the next point, when we were at 180 degrees, the y value was -1. If you times that by 2, it'll become -2. Okay, the point at 270 was at 0, so doubling 0 is still 0. And then at 360, when we were up at y value of 1, it's doubled, now up to 2. Okay, so we're going to have this exact same graph, same shape, I should say, right? It's just like taller, or it's vertically stretched. Okay, the fancy word we're going to use once we get more familiar with this, that is the amplitude of the graph. Okay, but for now, I just want to get comfortable taking the parent function and then kind of transforming it's what it's called. In this case, we just multiplied by 2. We vertically stretched it. So the final answer is the red one. The yellow one, again, was just a guide. You could either erase it or make sure it's real light. Make sure your final answer is clearly darker or indicated. Okay, and let's do one more. Okay, let's take a look at this one. Y equals -3 times the sine of x. So let's start out again. I'm going to graph the parent function, just ignoring the -3 for now. I'm just going to graph y equals sine of x, just to have that on my paper, okay? And then we'll be able to hopefully do the impact of the -3. So it's the same 90, 180, 270, 360. It's going to go from 1 to negative 1, just the parent function. And in this case, the parent function is just going to be using the y coordinates, right? So it's going to start out at 0, goes up to 1. Okay, at 180, we are back down to 0. 270 is when it hits its minimum of negative 1. And 360, we're back to where we started. Okay, so the parent function looks like this. Sorry for the sound effects. All right, so that's sine of x, and again, that's exactly what we just did over here, right? So you'll get real familiar with those, but at first I know it seems kind of weird and stuff, but again, everything's just based on the coordinates of this circle. Okay. All right, so that's sine of x. I should have done that in yellow, but anyway, so let's get the final answer in red here. What does y equals negative 3 times the sine of x look like? So what we're going to do, we are going to multiply, right? That's what's happening. This negative 3 is multiplied by the sine of x. So I'm going to take each y coordinate and times it by negative 3. Okay, so let's just do them one at a time. This first point here was originally at 0. If you multiply it by negative 3, it's going to stay at 0. Okay. The second point, when x is 90 degrees, you see the y value is up there at 1. If you times 1 by negative 3, this point is now going to have a y value of negative 3. Okay, the 180 y value was 0. It's going to stay 0 because multiplying by 0 stays 0. Okay, the point at 270 was negative 1. If you times negative 1 by negative 3, it's now going to be up at positive 3. And then the 360 was at 0 is going to stay at 0. So this graph now, okay, is going to go through those points. So it was actually reflected. Okay, see how the green one starts out by going up? That's what a normal sine does. If you remember, multiplying by a negative causes a reflection. Remember, like our parabolas, if it was negative x squared, it opened down. This is kind of just like that. And it also is much taller, right? Again, the midline, we're going to talk about all this stuff later, but the midline is still 0. It just goes up and down 3 from there, instead of the green graph only goes up and down 1. And that up and down distance is called the amplitude. And that's really what this number is going to be, okay? The amplitude of this graph would be 3, whereas the parent function would just be 1. Okay, so that's the impact on that. Let's get a little practice going, and we will keep building on this. Refer to the parent functions here when you're setting these up. Make sure you have these correct, and make sure we're okay. So hopefully that helps, and we'll get a little practice going. All right.